Recent astronomical surveys have begun mapping dark matter distribution with unprecedented precision. The Dark Energy Survey has created detailed maps showing how dark matter forms a cosmic web throughout space. Similar efforts from the Euclid Space Telescope and the upcoming Vera Rubin Observatory will further refine these maps, potentially revealing subtle patterns indicating influences from beyond our observable universe. As we'll explore in the next section, cutting-edge detection systems are being developed to directly search for these mysterious cosmic components. These sophisticated instruments may soon provide breakthrough evidence about whether dark matter and energy truly represent bridges to other universes, bringing us closer to future detection technologies on the horizon. What if scientists are developing instruments that might detect signals from beyond the supposedly impenetrable cosmic horizon? These revolutionary technologies completely reimagine how we observe the unobservable. When we discuss seeing beyond our cosmic horizon, we're not talking about conventional telescopes with bigger mirrors. The challenge requires entirely new detection paradigms that can capture indirect evidence of what might exist beyond observable reality. It's like detecting a storm beyond the horizon, not by seeing it, but by measuring subtle changes in wave patterns reaching our shore. Among the most promising approaches are next-generation gravitational wave observatories. While current detectors like LIGO and Virgo have revolutionized astronomy by detecting ripples in space-time from colliding black holes and neutron stars, they only capture relatively recent cosmic events. The planned Laser Interferometer Space Antenna, LISA, will take this technology to space, using 3 spacecraft flying in triangular formation, separated by 2.5 million kilometers, to detect much longer wavelength gravitational waves. LISA excites cosmologists with its potential sensitivity to primordial gravitational waves, ripples in space-time created during the inflation period immediately following the Big Bang. These waves would carry information from before the release of the cosmic microwave background, potentially revealing conditions that existed mere fractions of a second after the universe began. Even more ambitious is the proposed Big Bang Observer, BBO, designed specifically to detect the gravitational wave background from the early universe. By measuring the polarization patterns in these ancient waves, scientists might identify signatures of processes that preceded our Big Bang, perhaps even evidence of previous universal cycles or interactions with other cosmic domains. Quantum physics offers another avenue for detecting what lies beyond our observable universe. Researchers are pushing quantum experiments to increasingly macroscopic scales, testing whether quantum phenomena like entanglement maintain their strange properties across greater distances and with larger objects. If quantum connections truly transcend conventional space-time limitations, as some theories suggest, they might provide a window into realms beyond our cosmic horizon. Consider the quantum space telescope concept. Unlike conventional telescopes that capture electromagnetic radiation, this theoretical instrument would measure quantum correlations between particles that might reveal connections to domains beyond our observable universe. Some models suggest that quantum entanglement might connect particles across different universes or through extra dimensions, potentially allowing indirect detection of what exists beyond our cosmic boundaries. Researchers at institutions like the Institute for Quantum Optics and Quantum Information in Vienna are already performing sophisticated tests of Bell's inequality, the mathematical relationship that distinguishes quantum mechanical systems from classical ones. By extending these tests to cosmological scales, scientists hope to determine whether quantum connections could provide evidence of cosmic domains beyond our observable universe. Particle physics presents a third powerful approach to probing the cosmic unknown. While the Large Hadron Collider at CERN has transformed our understanding of fundamental particles, future accelerators might reach energies sufficient to produce phenomena predicted by theories about what exists beyond our universe. The proposed Future Circular Collider, FCC, would dwarf the LHC with a 100-kilometer circumference, potentially reaching energies up to 100 TeV, energies that haven't existed in our universe since shortly after the Big Bang. At these extreme energies, physicists might detect evidence of extra dimensions, produce microscopic black holes predicted by some string theory models, or identify particles that could serve as messengers between our universe and others. Meanwhile, astronomical surveys are achieving unprecedented precision in mapping our observable universe, potentially revealing subtle anomalies that might indicate interactions with cosmic domains beyond our horizon. The upcoming Euclid Space Telescope and the ground-based Vera-C Rubin Observatory will map billions of galaxies with extraordinary precision, creating three-dimensional maps of matter distribution throughout cosmic history. These ultra-precise maps might reveal unexpected patterns or alignments in cosmic structure that current models can't explain, potentially indicating influences from beyond our observable universe. Particularly intriguing would be evidence of non-Gaussian features in the distribution of galaxies or in the cosmic microwave background, statistical patterns that might indicate interactions with other universes during cosmic inflation. Some researchers are developing specialized instruments to search for specific signatures of multiverse interactions. The CMB S4 project will deploy multiple telescopes at the South Pole and in Chile to measure cosmic microwave background polarization with unprecedented sensitivity. These measurements could potentially detect bubble collision signatures, circular patterns in the CMB that might indicate where a universe physically contacted another during its formation. Theoretical physicist Matthew Johnson and colleagues have developed sophisticated computer simulations of what these bubble collision signatures would look like if our universe had indeed collided with others during its early expansion. By comparing these theoretical patterns with actual observations, scientists might find indirect evidence of universes beyond our own. The ultimate limitation in all these approaches remains the cosmic variance problem. With only one observable universe to study, distinguishing rare statistical fluctuations from genuine signals of beyond-horizon physics presents an enormous challenge. This has led some researchers to propose studying universes in a lab, using quantum simulators or advanced computational models to create artificial systems that mimic cosmic evolution under different physical laws. What unites all these approaches is a fundamental shift in scientific methodology when confronting cosmic boundaries. Rather than direct observation, scientists rely on mathematical consistency, indirect signatures, and statistical patterns to infer what might exist beyond our observable universe. This represents the greatest strength of scientific inquiry, the ability to develop testable predictions about phenomena that seem permanently beyond direct detection. Philosophical frontiers, redefining reality. Beyond the technical challenges of detecting other universes lies an even more profound question. If multiple universes exist, each with different physical laws, is our reality just one arbitrary possibility among countless others? This possibility expands our cosmology and completely reframes what we mean by existence. Philosophy has wrestled with questions of reality for millennia, but multiverse theories introduce unprecedented complications. When physicists propose infinite parallel universes, they challenge our most basic assumptions about what constitutes reality itself. These theories force us to reconsider whether our universe, with its particular set of physical laws, represents anything special or necessary. The philosophical implications begin with ontology, the study of what exists and how it exists. Traditional ontology assumed a single coherent reality governed by universal laws. Multiverse theories suggest instead that reality might be fundamentally plural, with our universe representing one manifestation among countless possibilities. This transforms existence from a binary state into a spectrum where different universes might exist in different ways or with varying degrees of reality. What happens to our concept of reality when it becomes merely one arrangement among infinite others? Consider our universe's apparent fine-tuning. The fundamental constants of physics, like the strength of gravity, the mass of electrons, or the strong nuclear force, appear calibrated with extraordinary precision. If any were slightly different, stars couldn't form, chemistry wouldn't work, and life, as we know it, would be impossible. This fine-tuning presents a striking coincidence that demands explanation. The traditional explanation invoked design. Some higher intelligence precisely calibrated these values to enable life. But the multiverse offers an alternative: selection bias. If infinite universes exist with every possible combination of physical laws, then universes capable of supporting observers would be rare, but inevitably, observers would only exist in those universes capable of supporting them. We find ourselves in this precisely tuned universe not because it was designed for us, but because it's the only type where we could possibly exist to ask the question. Philosopher of physics Tim Maudlin suggests this transforms our understanding of what requires explanation. In a multiverse scenario, he explains, the apparent fine-tuning of our universe is no more surprising than finding yourself on Earth rather than floating in deep space. Of course you're on Earth. You couldn't survive anywhere else. This perspective, formalized as the anthropic principle, shifts the explanatory focus from why these specific values to why a multiverse with varying values. Yet this solution creates new philosophical challenges. Traditional scientific theories aim to be both explanatory and predictive. The anthropic reasoning within multiverse theories provides explanations but struggles with predictions. If literally anything is possible somewhere in the multiverse, do we risk creating a theory that explains everything and therefore explains nothing in particular? Philosopher Karl Popper argued that scientific theories must be falsifiable, capable of being proven wrong through observation. But how do we falsify claims about universes beyond our observation? This leads to debates about what separates legitimate science from untestable metaphysics. Multiverse theories also transform our understanding of causality. In classical physics, every effect has a specific cause that precedes it. But in quantum multiverse models, events might have causes that exist in parallel branches of reality, a radical departure from our intuitive understanding of cause and effect. Imagine reality as a cosmic kaleidoscope, where each twist reveals patterns that influence each other across dimensional boundaries. The boundary between mathematics and physical reality becomes particularly blurred in multiverse theories. Mathematical physicist Max Tegmark proposed that mathematical consistency isn't just how we describe reality, but is reality itself. In his mathematical universe hypothesis, Tegmark suggests that any mathematically consistent structure exists in the same sense our universe exists. This implies that mathematically coherent universes possess a form of existence independent of observation. This view challenges the traditional distinction between what's real and what's merely theoretical. If mathematical structures have an independent existence, then the equations describing other universes become windows into genuine realities. As physicist Eugene Wigner noted, the effectiveness of mathematics in describing our universe might be essential. Reality is fundamentally mathematical. These perspectives transform our concept of consciousness and personal identity. If infinite universes exist containing every possible variation of ourselves, what becomes of the continuous self? How does personal identity function across diverging quantum branches? The ethical implications are equally profound. If every possible decision happens in some branch of reality, what becomes of moral responsibility? Some philosophers counter that even if all possibilities occur somewhere, our decisions still determine which branch of reality we experience, preserving moral agency within our particular cosmic branch. Perhaps most fundamentally, multiverse theories challenge the relationship between science and meaning. If our universe is one arbitrary possibility among infinite others, does this diminish its significance? Philosopher Thomas Nagel suggests this might create an absurdity with a significance we find in our lives' conflicts with our cosmic insignificance. Yet others find new meaning in multiverse models. Could the existence of every possibility transform how we think about potentiality and actuality? Rather than seeing unrealized possibilities as abstractions, we might consider them as concrete realities in other cosmic domains, connecting us to a broader fabric of existence. The boundaries between physics and metaphysics blur in these discussions. Questions once considered beyond science, like why does anything exist at all, now intersect with theoretical physics, requiring scientists to engage with philosophical questions they might have previously avoided. We've journeyed from quantum scales to cosmic boundaries, from mathematical models to philosophical implications. But this exploration isn't an endpoint, it's a beginning. The frontier of our cosmic horizon represents the edge where observation ends and theoretical exploration begins. What's truly remarkable is how we've developed frameworks to conceptualize what might exist beyond our universe despite fundamental observational limitations. Our quest evolves as new instruments and theories emerge, pushing back the boundaries of the unknown. The greatest insight remains that knowledge itself expands as a dynamic frontier, growing alongside our understanding of cosmic reality.